In this video, we're going to study the orthocenter of the triangle. So suppose you have a triangle, and you draw the three altitudes in the triangle. They always intersect at a single point. And this is what we're going to prove today. This point here, the intersection of the three altitudes, is called the orthocenter of the triangle. So essentially what we need to prove is that if we construct this line defined by this point and this point, then the angle that it makes here is 90 degrees. So we need to prove that this line is perpendicular to this line. First, suppose that this angle here is beta. We're going to prove that this angle here is 90 minus beta, and then it would follow that this angle is 90 degrees because the sum of the angles in this triangle is 180. Now we have that this angle here is 90 minus beta because of the sum of the angles in this triangle. Then let's notice that we have some cyclic quadrilaterals here. For example, this one is cyclic because we have a right angle here and a right angle here. And these two angles are equal. And now because of the cyclic quadrilateral, we have that this 90 minus beta equals this angle here, also 90 minus beta, because both of them point towards this side. Also, this quadrilateral here is cyclic, because the two opposite angles, this angle is 90 and this angle is 90, so their sum is 180, and therefore it's cyclic. And because it's cyclic, this angle here equals this angle here. So because this is 90 minus beta, this one is 90 minus beta. And that's it. We proved that this angle is 90 minus beta, and since this is beta, then this is 90 degrees as desired. Now that we've proved the orthocenter, we can find some more properties. For example, this quadrilateral here is cyclic because of these two right angles. This quadrilateral here is cyclic, again because of this angle is 90 and this angle is 90. This quadrilateral here is cyclic, again, this 90 and this 90. And this quadrilateral is also cyclic. Here's 90 degrees and 90 degrees. And from here, we can actually find the angles in this triangle. Because, for example, from this cyclic quadrilateral here, we have that this is 90 minus beta, and therefore this one here is also 90 minus beta. Note that this line is an angle bisector of this angle here. And similarly, we can find the other angles of this triangle, here, 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 and here, and it will turn out that this is an angle bisector of this angle, this is an angle bisector of this angle, and this is an angle bisector of this angle. So the three angle bisectors in this triangle intersect at this point, which is the orthocenter of the large triangle. Here's how the full picture looks like. These angles here are 90 degrees minus alpha because of the cyclic quadrilaterals here and here. And these angles here are 90 degrees minus gamma because of the cyclic quadrilaterals here and here. And these angles are of course 90 minus alpha, assuming that this is alpha. And these angles are 90 minus gamma, again assuming that this angle here is gamma. One more thing to notice here is that since this is an angle bisector, then this is the external bisector of this angle, because always the angle between the internal and the external bisector is a right angle, is 90 degrees. And here we have 90 degrees and an internal bisector. Therefore, this is an external bisector. An external bisector basically means that this angle equals this angle. And you can see it's true, of course, because if this is 90 minus beta, then this is beta. And if this is 90 minus beta, then this is beta. So these two angles equal beta. And same thing for here. This line is an external angle bisector of this angle. And this line is an external angle bisector of this angle. And so for this triangle, these are the internal bisectors, and these are the external bisectors. But what if the triangle we started with has an obtuse angle, such as this one? So an angle that's larger than 90 degrees. What do we do? Where is the orthocenter in this triangle? Well, let's see. The first altitude is defined by taking this point and constructing a perpendicular from this point to this opposite line. The second altitude is defined by taking this point and constructing a perpendicular with respect to this side, the opposite side in the triangle, to this vertex. So we extended the side a little bit so we can construct the perpendicular. And the third altitude is defined by taking this point and constructing a perpendicular to this side. And so it would look something like this, and it would intersect the other two altitudes at the same point. So now let's try to prove that this angle here is 90 degrees. Well, instead of considering this triangle as the initial triangle, let's consider the larger one, this one, as the initial triangle. In this triangle, this is an altitude, and this is also an altitude. And therefore, this point is the orthocenter of this triangle. And therefore, if we connect the orthocenter with this vertex, this is going to be a perpendicular here to the other side, because the orthocenter is the point where the three altitudes intersect. And in conclusion, the orthocenter for an obtuse angled triangle, such as this one, lies somewhere outside of the triangle, so outside of the initial triangle here. And of course, in a triangle with a right angle, one of the altitudes would be this, it would coincide with the side, and the other altitude again would coincide with the side of the triangle, and the third altitude will be this. So again, the three altitudes would pass through the same point. So in this case, one of the vertices of the triangle is the orthocenter. Here is the optional problem. We have a triangle, and we drop two altitudes, like this and like this. We intersect them here, and then we take this line, and we intersect here. Then we drop perpendiculars from this point to this line here, to this line here, to this line here, and to this line here. We need to prove that the feet of these four perpendiculars lie on a straight line. And here's the solution. I'm sure you immediately spotted the first step in the solution, because we have two altitudes here and here, and so this is the orthocenter of the triangle, and therefore this is the third altitude, so we can mark this angle here as a right angle. We're going to prove that this point, and this point lie on the same line. And by symmetry of argument, we can prove in the exactly analogous way that this point, and this point lie on the same line. And by symmetry of argument, I mean that the way this point is constructed is entirely symmetric to the way this point is constructed. Instead of with respect to this side, it's a perpendicular with respect to this side. And so if an argument works for proving that this point lies on the line defined by these 2 points, then the same argument would work for proving that this point lies on the same line. First of all, let's denote this angle by beta. Then this angle here is 90 minus beta, because this is 90 degrees. But now this here is a cyclic quadrilateral, because we have a 90 degrees here and 90 degrees here. And so this angle 90 minus beta comes here. Now essentially what we need to prove is that this angle here is 180 degrees, which would mean that this is a straight line, because 180 degrees is a straight angle. And we have 90 minus beta here and 90 here, so it suffices to prove that this angle here, the remaining one, is beta. Now consider this quadrilateral here. It is cyclic because we have a 90 degrees angle here and 90 degrees angle here, and therefore if this is beta, then this angle here would be 180 minus beta, and so this angle here would be beta. Finally, consider this quadrilateral here. It is cyclic because this angle is 90 degrees and this angle here is 90 degrees and their sum is 180, and therefore this angle beta equals this angle here, so this angle is also beta, and that's it. Now this angle here is 180 degrees, and therefore these 3 points lie on a straight line. Now by symmetry of argument, this line also passes through this point.